Do you have any specific questions you want to ask about other material or this material? Okay. This says that I can do a live voice transcription in my native language or a different language. I might choose like French or I don't know, just like do some random language. That'd be crazy. Like it's like transcribing and translating at the same time. That's cool.
That is great.
Yeah. Okay.
I wonder how accurate it is though.
No idea. No idea. I'm assuming it's probably not like super accurate, but then again, with AI in the past few years, maybe it's pretty good. Never know. Okay, let me test this out. I think these problems are not too bad. I solved them all in like probably 45 minutes today, so cool. That works. Okay. Okay, yeah. So he gave me 3 problems. This one is a conservation of, well, this is an energy problem. And then we have a conservation of momentum problem and a conservation of mass problem. And I guess he said on the exam, you'll have 1 problem from the previous exam material, something like that, and then or however many from the new material. So, okay, so this one says that we have a turbine and it's extracting energy from a lake, I guess, penstock. And when we look at this, we can kind of look at this h, this height distance there, as like a level 1 and level 2. If you want to think about like what's the kind of beginning and end points for this problem. So, okay, so I'm gonna write my givens first. Okay, so we have a friction head loss that is equal to CQ squared, where C is a constant. That depends on the penstock geometry and water properties. So we'll just leave it as C. We don't need to really know anything about it, but that's just, it's a constant. And then we know that we have what's on the figure. So I'll just say maybe figure quantities. Okay. And we want to know and we know that Q is the river flow rate. Okay, so we want to know or I guess we want to prove that the max power is equal to 2 rho g h q divided by 3, and that it occurs at a river flow rate equal to h divided by 3c, where 3c is, that's all in the denominator, and then that's square rooted.
This one's just like deriving equation,
Mhm.
kind of.
Mhm.
Okay,
Yeah, this one's basically derive the equation and prove that that's what you get.
yeah.
Yeah.
I was looking at that, I was like, what am I trying to find?
Right, right.
I was like,
Yeah.
no numbers. Okay, that makes sense. Okay.
Yes. Yeah. This one's basically you derive it, and if you get that, you kind of know that you're right because you're supposed to prove that that's the case. So for the solution, okay. So the way he does this one is he applies the energy equation or Bernoulli's equation to this. So if we think about or at least they're very similar. So I kind of think of it as Bernoulli's equation. It's the energy equation, but they're very similar. So we have, and we're going to say from 1 to 2, like I marked on the figure. So then that equation is P1 over rho G plus V1 squared over 2G plus H1 is equal to P2 over rho G plus V2 squared over 2G plus, actually I miswrote this. This is Z1, and then this is going to be Z2 plus the friction head loss plus the turbine head. Does that look familiar?
Just like until Z2.
Just this part?
Yeah.
Yeah.
But
So
you said it's like also the energy, so it's like similar.
yeah, so I guess that's what I meant by Bernoulli's equation. This part here is what we saw as Bernoulli's equation last time. So I don't know if you still call it Bernoulli's equation when you add on the H's there. But he called it the energy equation in his solution. Yeah. So when he named this in his solution, he just called it this. But it's basically Bernoulli's equation with those two add-ons. And so that's why I said it's like, that's how I think of it. But okay. So what do we do with that? So we
Real quick.
yeah.
So for the H's, how do you
Mhm.
know which ones to add? So
Right.
like if I like let's say like I forgot the H for the turbine. Is it like if I had something else on the diagram,
Mhm.
if that makes sense. Like how do you know what to account for?
Okay. So you're saying like what if you had like another device or something?
Yeah.
Okay.
Like I'm thinking like if I was in a test scenario and
Mhm.
like let's say they gave me the head loss, but I totally forgot about the turbine one.
I gotcha. Okay. Well, I guess if I suppose that we include this one because there is a turbine involved.
I guess the right question would be like, what else could there be?
Oh, like what other devices
Yeah,
could he
so
come
like,
up with?
like if I was
Mm.
okay, so I know there's HVAC, I know there's a turbine here, and I know there's this here.
Okay.
Like how
Right.
many possible ones could I put?
Well, that's a good question. I'll ask him.
Okay.
What other kinds he could doctor up?
Yeah.
Yeah. I'll mark that down and ask him. I mean, in this case, it lists HF, so like this one's listed, which is why I would include it. And then the other one we have a turbine, so then I would say that you see the turbines, then you have that head loss. But as far as like what other kinds he could come up with, I'll ask him that. So
I'm asking a lot because I know this test is coming up.
yeah, no, ask as many questions as you want. I think these are pretty, as far as the solution goes, they're pretty quick. So like if you have questions, just yeah, for sure, ask me. Yeah. Okay. So anything else there with that? Okay. So then the next thing we need to do is apply some assumptions. So if this is 0.1 and 0.2, you know, 0.1 is kind of like saying we're right here at the free surface. 0.2 is we're like right here, also at a free surface. So would you agree that pressure 1 and pressure 2 are both atmospheric pressure?
Yeah.
Okay. So then that's assumption 1. So we know that P1 equals to P2 equals P atmosphere. So then that cancels and that cancels. And then would you also agree that if we think about this 0.1 being like a lake surface and 0.2 being like a lower lake surface or a pond, let's say, that the velocities at those 2 points would be 0?
Oh, yeah.
Right, because it's just like a still lake.
Yeah.
It's kind of weird to think about like that, but if you think about the outer, not the flow inside the channel, but like the very beginning, very end,
Yeah.
we have, so that's the second velocity, or that's the second assumption. There's, both of those are 0 velocity. So V1 equals V2 equals to 0 meters per second. So then these, that and that cancel. So that, oh, and then if we say that for a reference point, if we say that like point, let's say 2 is our like 0, then we can say Z2 is 0 and Z1 would be H.
Yeah.
Right. So if we say this is kind of like our 0 point going that way, then we can say that this is 0 and that is H. So then we can rearrange this guy and say that H turbine is equal to, yeah, H minus HF. So simplifies to that. And then if we go and plug in HF from the other slide, we know that HF is CQ squared. So this would be H minus CQ squared. Okay. And then we're trying to derive the max power, right? So he gives the equation for power as rho G Q H turbine. Is that familiar?
Yeah.
Okay. So yeah, because I had to ask him about like where did that come from, basically. So, but if that's familiar, then that's good. And I guess, well, I'll just do this just for anyone else who might be kind of wondering about that. But rho Q, you could rewrite that like this. Let me write it like.
And this is power of the turbine, right?
This is the power of the turbine. Right.
Oh.
Yes. Power of the turbine. And so you could think of this in terms of like a rho QGZ, where Z is a height. So this would be like m dot GZ. And then you could think of that as mass over seconds GZ. So this would be like mgz over seconds, where this is like, you could think of this like potential energy, kind of, divided by time equals to power. So that might just be helpful, just like understanding how that gives you power. That's the, yeah, so that was good for me. Okay, so this is power of the turbine, yes. Okay, so if we go ahead and plug in H turbine, then we're going to get power is equal to rho GQ times H minus CQ squared. And then if we just distribute that, then we're going to get rho GHQ minus rho GCQ cubed. Okay. So that's our power equation. Now to find, if we want to know max power, we'll take the derivative and set equal to 0, right? So thinking about like a curve, and we're looking for that max derivative there, or the 0 derivative indicating max power. If this is like a XY graph. Okay. So then if we were interested in the flow rate, right? That's kind of our fundamental quantity here we're measuring this power against. So we're going to derive with respect to the flow rate. So then this is going to be rho GH minus 3 rho GCQ squared. And then we want to set that equal to 0 to get the maximum. So then this would be 3 rho GCQ squared equals to rho GH. Cancel the rho G's. And then we'll get, there we go. We'll get Q is equal to the square root of H over 3C. So that is the answer of making sure that max power occurs at that flow rate.
Oh.
That's that answer right there.
Can you plug that back into the original one or no? Not yet.
So you will plug it back into the power equation.
Oh, okay.
So if we know this is proved flow rate for the max power, then to get the max power, we would just plug it back into the power equation. So P max is going to be this power equation right there. And then, which I'm going to plug it into the undistributed format. So it's be rho G. It's weird the way he does it. You also have to trust me for a second. I'm going to leave that Q there. H minus C, but this Q squared, I'm going to plug in. I don't know why the solution's like this, but it may not have been him who did this. It might have just been like the way the book did it for some reason. But he plugs in the Q for Q squared, but not for Q. And then what you get is rho G Q times, what will this be? H minus exactly. You get that? And so the answer is rho GQ multiplied by 2/3 H. And that is the answer for Pmax.
I guess it's just like figuring out what the question was asking for.
Yeah.
I guess that's why, yeah.
Yeah, I think that one's challenging. It's like, what equation do you apply? I think energy equation is, we don't really see any forces going on. So conservation of momentum would be kind of like, why would you use that? There's no forces. And then conservation of mass, it's like, well, yeah, is there any like conversation about mass transport or something like that? And so you might think, well, we have this like elevation difference. We have this turbine that's producing energy or converting energy. And we have this water, flowing. So then maybe the energy equation applies best. Yeah. And then also just looking at that and being like, that's why I always write my givens first. It's just to get a handle on, by reading it through and then writing the givens, it gives me time to like kind of chew on it for a second and be like, what might it be asking for? And in this case, you're proving, yeah, it's a different type of problem for sure. Yeah. Okay. Do you have any questions about that?
No.
You could have plugged in Q there too and had just the same answer. For some reason, he just didn't. So.
But I guess it's just like recognizing how to like get it from that to what they were asking for.
Right. Which they didn't even ask for this Q to be there. For some reason, it just is.
Oh.
So I don't know. Like you could plug in Q and it'd be just as correct. I don't know why. I maybe just make it look cleaner. They just didn't plug in Q, but it seems weird to me to solve for that Q and then not plug it in. So, yeah.
It's not like it's simplest part, I guess.
Right. Exactly.
Yeah.
Exactly. Yeah. Okay. So next problem. So this is a wedge. We have water that is being, a jet of water is flowing over the tip of that wedge and being split. We have an assumption here that it's a symmetric split. Yeah, so it's even. You don't have to worry about like the top flow being more or less than the bottom flow. And that comes in very handy. So then if we write our givens, we know we have water at 20 Celsius. 20, not 209 Celsius, that'd be wild. And then we know we have, so it's basically saying that into the paper, the depth is very large. So the reasoning there is, when you see something like that, it's like wanting you to get work in per unit depth. So it's saying like, that might be like 200 meters or something. We don't know, but so you don't want to work this in per unit depth as you go through the problem. We know that there's this force of 126 newtons that's required to hold the wedge in place. And so it says find theta. Okay, and then we have the figure too. Whatever's on the figure, quantities. Okay, so then solution.
Would you start with like that force equation where it's steady state?
Mm-hmm.
And then, okay.
Yeah, so that's actually another assumption we have. Yeah, that's a good point. So we have this is a symmetric split, and it's also steady.
Okay.
Yes.
I'm just trying to work it with you. So like...
Yeah, no, that's actually good because that's gonna be better for your learning anyway. So that's good. Feel free to keep doing that. So yeah, so this will be, we're starting out with we're starting out with this sum the forces in the x direction is equal to that ddt integral rho v d dv plus the summation of m dot I vi out minus the summation m dot I vi in. Is that the one you meant? You're talking about? Yeah. So exactly. So this goes to 0 because it's steady state. And then if we, I guess, simplify this, start plugging in quantities, then we can say that, well, and I'll make this note too, we're only in the x direction because symmetric flow. So basically Fy, the forces in the y direction cancel. So that's why that assumption is important. So we can just do x direction. So then this is going to be that forces in the x direction is that negative F force because it's going to the left. And then that's assuming, so I guess we're assuming that positive x is to the right. So then that's negative F. And then we have our m dot in is going to be, our m dot outs are going to be, if we call this 2 and this 3 and that 1, let's say, then this will be m dot 2 v2 plus m dot 3 v3 minus m dot 1 v1. So then what we have to recognize is that because this is like a symmetric flow, then v2 will equal v3, which is going to be equal to the velocity times the cosine of theta over 2. Since this is since theta is like that whole angle. So I'm going to write it out just so for people later in case they're curious. But theta over 2. Okay. So then what we can also realize is that if we apply the conservation of mass, then m dot 1 must equal m dot 2 plus m dot 3. Right. But if it's symmetric, then m dot 2 and m dot 3 are equal to each other, right?
Like m.1 equal like 2 m.2.
Exactly. 2 m dot 2 or 2 m dot 3, however you want to think about that. So this is all kind of like a, I don't know, just kind of thinking this through. Okay. So with that in mind, we can rewrite this equation. I'm going to start a new page here. So we can rewrite this as negative f is equal to m dot 1. And what I'm going to say is I'm going to call this here just v, just velocity. Okay, since we only had the 1 in this problem. So then this is just v, positive, right? Because we're going to the right. And then we're going to have hang on, I flipped my signs here. Yeah. I flipped my signs. So let me just rewrite the equation first. So we have m dot 2, what's that, v2 plus m dot 3 v3 minus m dot 1 v1. Okay. So then this negative f is going to be equal to, we can sub in m dot 2 here. So m dot 2 v2 plus v3 minus m dot 1, and this is that positive v I was talking about. Okay, and then we can say that this is going to be v cosine of theta over 2 plus v cosine theta over 2 from the discussion before. Oh, wait. V. And then, so this would be negative f is equal to m dot 2 times 2v cosine theta over 2 minus m dot 1 v v.
And then could you also sub in the 2 m.2
Mhm.
as well?
Exactly. So then that quantity there is just m dot 1.
Oh, okay.
Right. Is that what you meant?
I meant the other way, but that also works.
Oh, yeah. So, yeah. Right. I guess you could do it either way. Yeah, I'm just going to do it this way, and then we'll solve for because we don't know what m dot 2 is. Well, we know m dot 2 is, yeah, it's just easier to solve for m dot 1, basically, because we know more about this flow here.
Right.
So then solving for that's easier. So yes, so this will be negative f is equal to m dot 1 v cosine theta over 2 minus m dot 1 v. And then so then this is so we can factor out m dot 1 v and get cosine theta over 2 minus 1, right? And then yeah, so then we just have to go ahead and solve for our theta. So if we solve for theta, we'll get negative F divided by m dot 1 V plus 1 is equal to cosine theta over 2. Okay. So we will go ahead and I'll go and plug in numbers at this point, make it a little easier. So this would be negative 120, 126. Oh, I messed up here. So this this force, if you notice in the problem statement, it says it has N for newtons, but then it says per meter of depth.
Oh,
So this is actually newtons per meter. That's kind of like a little trick for this problem. So this is actually newtons per meter. I just didn't say that before, or write it correctly. But so we have 126 newtons per meter, and then our m dot exactly. So he said just take density as 998 kilograms per meter cubed, which comes from your temperature of your water.
and then he's giving us like the chart again, right?
I would assume so. Yeah, I would assume so. In the problem, he just gave me the density in the solution and just said assume it's this, but I would think that he'll give you any chart you need, unless he tells you to print it out and bring it yourself. But yeah, if he hasn't said that, then I would think he'd give it to you. And so we have that. Then it's a right rho GA. So then our G or no, sorry, rho VA. So our V is what does it say 6 meters per second. And our area is this is a rectangular kind of profile. So, but we're also looking at this. Well, it is a rectangular profile, but we're looking at per unit depth, right? So if this is, so m dot is rho VA, but if we say that the depth here is B into the page, then m dot over B would be rho V, and whatever you want to call that, this guy. Yeah, H maybe, or L. So this would be rho VL. Yeah, because everything in this problem is per unit depth. So our force is per unit depth, and so then our mass flow rate we need per unit depth.
Okay.
So the units all worked out.
Okay.
So this will be rho V and L is at 0.04. Was it 4 centimeters? Yeah. Okay. And then there's 1 V. I didn't allow enough room here. So there's an extra 6 meters per second here. Is that clear or should I rewrite that? Maybe I'll. Yeah, I'm gonna rewrite that just so it's clear. But so it's 998 kilogram per meter cubed times 6 meters per second times 0.04 meters. There we go. So this is that one, and this is that other V. This is m dot 1 per unit length. Or depth, I'm sorry, depth. depth, which is B. Yeah, that's not the clearest thing I've ever done.
I get it.
Yeah.
It's just it was kind of tricky the way he worded it in the problem. There was like the units per meter. I probably wouldn't have got that.
Yeah, the way the problem worded it is weird because it doesn't. It's like it splits the units up between
Yeah.
verbiage and symbols. So yeah, that part is weird. I'm gonna say it like this: m dot. So m dot is rho VA. M dot one is m dot per unit length, per unit depth, which is rho VL. Need to work in per unit depth for units to work out. Cancel. Okay. So if you do that, this will give you cosine theta over 2 is equal to 0. 0. Oh, wait, and there's a plus 1.
I know you didn't have any.
Yeah. Let's see. There we go. Plus 1. This will give you that. And then if you take the inverse cosine, that's going to give you, I was going to go to the solution. That will give you 48.43 degrees. That's your theta. Cool. All right.
I think he'll be okay on the test. It was just the wording of it. So
Yeah.
You can make it as complicated.
Yeah. Sometimes the wording is what gets me. Because I used to like when I was in like dynamics and thermo and all those kind of classes, the wording is tricky, to so that's why I would like read it through completely one time and then go back through it and write everything I know. Something about that would help me digest like what's there and kind of start thinking before I start trying to do stuff, start thinking about where might I go with it, and then just like pick a path and start going. And if it doesn't work, then reevaluate and try something else. But that's just the way I worked problems, or still do, I guess.
Did you go back to the question for this one?
Yeah.
So how would you know, like, that it's the area of it was rectangular? Because I assumed it was like
Circular.
Yeah, I assumed it was coming out of a pipe. That was just like my assumption.
Yeah, I think that it's this here. It's that assumption. Yeah, because if you see that it says a sheet of water. I don't know how you would. Yeah, I mean, I guess a sheet of water is probably like, something like that.
Okay. I just have to pay attention to that.
Yeah, it's just the verbiage is probably what's going to tip you off. And then if it says it's like very long into the paper per unit depth, it'd be hard to imagine unless you have like an oval flow.
Yeah.
It'd be hard to imagine it's like circular-ish. because a circle is not going to be like very far into the depth.
Oh, okay.
You know what I mean? You'd have to stretch that circle into like an oval. So it's once you go per unit depth and have this very like wide flow, it's probably easy just to say it's rectangular.
Okay, I misunderstood the very long into the paper. I thought it was like the other side of it.
Oh, oh,
That
you mean like this
makes a lot
way?
more sense, yeah.
Oh, okay. Yeah. So this here is it's like it's saying it's way. I don't know if that's easy to imagine. It's like saying it's like that.
Right, and then you were saying you just wanted to look at that like one area.
Right, but we're just studying the kind of like cross section
Yeah.
or the side view, you might say. Yeah. Yeah. So we are evaluating side view. Maybe that will help anyone else who's doing this. I'm going to erase that. Okay. Cool. Anything else on that one that I could explain better? Okay, cool. All right, last problem. This is also the shortest one, I think. So we have a flow coming over this ridge. That dotted thing is like a porous soil or something like that. So the water is coming over and being absorbed down into the soil. So this again is so here it says 5 meters deep into the paper. So that kind of like the previous problem is sort of an indication that we have this like rectangular flow that's 5 meters deep. So then, you know, down here, it'll also be 5 meters deep. The whole problem is just like that. So then we know that the depth, I'll call it B, is 5 meters. We know if we say this is like our section 1, and then down here is like section 2 or something of that nature, our inlet velocity is going to be, well, maybe it's best not to think of this in terms of sections. I'm just going to call the velocity in. So V in is going to be 2 meters per second. We have an initial depth. I'll call that L. L in is equal to 0.2 meters. And that depth is, well, maybe that's confusing. I'll call this width, just to make that clear. Width is, yeah, it's the height.
Okay, yeah.
Yeah.
I was like,
It's before we said depth was like into the page. This one's wording it as, here we're saying depth is the height of the water.
okay.
And then I'm going to say into the page is the width of the flow. So, and then we know we have this like, it's absorbing into the porous material. So I didn't really know what to call that. I said it's like a dot absorption rate. I came up with that, just absorption rate, just to give it a symbol. But the units, it's a 8 millimeters per second, and or 0.008 meters per second. So this is really like a velocity. I just called it A dot. Okay, and we want to, and then we know we have the figure quantities. Okay, so then we want to find capital L, which is the length of the bed. It's this distance here. That's L. Okay. Oh, and it says L to completely absorb the water. So when you hear that, what does that make you think? Completely absorb the water.
Like it would basically how much water is in it, it would just take it immediately.
Exactly. So this is a steady problem.
Oh, okay.
Yeah, so it's saying that whatever is coming over that ridge is getting soaked up just as fast as it's coming over.
Okay, like on
So-
contact, kind of.
Exactly. Yeah. So then there's basically no mass accumulation because everything that's coming in is being absorbed. Granted, we're finding the L so that that is the case.
Yeah.
So what does L have to be so that all this is absorbed at a rate to match the inflow and have a steady, no mass accumulation type thing. Steady state. So I'll say that this is steady state. Cool. Okay, so for the solution, so this is going to be a conservation of mass problem. For a steady state scenario, then we know that based on the conservation of mass, that m dot in is going to equal to m dot out, right? So then that means that rho VA in equals to rho VA out. So then we can just plug in some, I guess, quantities here. So we know that the rows will cancel. It's all water. This velocity is Vn. This velocity is A dot, our absorption rate. And then, yeah. So we can rewrite this as Vn, the area of the inlet flow is going to be what did I call that? I said that that was Ln, the initial depth, multiplied by, I called it B, right? Yeah, the width B. And then equals to A dot times L times the B. Okay, so the B's cancel. Solve for L. L is Vn Ln divided by A dot. Which is 2 meters per second times 0.20 meters divided by 0.008 meters per second. Cancels some units, and that will give us 50 meters. So that's that. That's what L equals to. Cool. Yeah, that one's pretty straightforward. That's a nice one. Yeah, kind of a unique scenario, I've never really, maybe I've seen a problem like that before. Maybe, I don't know. Maybe I have, but yeah. Do you have any questions about that? Okay.
I guess my only question is like the B part.
Yeah.
Because like the length in is like the height, kind of.
The length in is the height.
Yeah.
So you're saying this?
Like from the wall to down to like the soil or something, like the porous bed. Is that the length?
Oh, you're saying this?
Yeah.
That's not used at all.
Okay, that's what I was like.
So are you saying this length, or when I say we say length, you don't know this?
Yeah, that one. So that length is like
That's this. That's this. So it's this initial depth. What it's trying to point to is this height here.
Okay.
Yeah. So it's saying that, yeah, this rectangular area, one side is 20 centimeters, and then it's 5 meters into the street.
Okay.
Yeah. Yeah, that is confusing because this is just the flow line, but that's not like it kind of looks like it's like a bracket saying that's the height, but it's not. That's just the flow, and then but the height is there.
Okay, that's great.
Cool. Well, I think it's 7 right now. So, all right.
Anything with like the conservation maps that they help you get on.
Yeah, conservation of mass is nice. And it's kind of cool that conservation of mass is very, very similar to conservation of momentum. It's just ever so slightly different. So, yeah, you can kind of.
Is one I'm gonna have to like look on a little bit more.
Yeah, for sure. All righty. Keep those.
I don't have that lab.
You what?
I have to do my math lab report.
Oh, I thought you meant you have a lab right now. It's like,
No.
man, that's a late lab.
No, that's what she was in my group, so that's what she was saying.
Oh,
She was
okay.
gonna go work on that.
Gotcha.
Yeah, I gotta do that part too.
Yeah.
Thank you for answering all my questions.
Yeah, no problem. If you have more questions, let me know.
Thank you.
Yeah, you too. See ya.